The 1970s. Astronomers around the world are beginning to notice something strange in their data. They are measuring the velocities of galaxies, the speeds at which galaxies in the local universe are moving relative to our own. The number for each galaxy should follow a simple pattern. The further away the galaxy, the faster it recedes, in proportion to the rate of cosmic expansion. Small variations are expected, driven by local gravitational interactions, but the overall pattern should be smooth, predictable, explainable. The numbers are not smooth, they are not random either, that would be easier to explain, they are systematic, coherent, galaxy after galaxy, across a large region of the sky, showing velocities that deviate from the predicted expansion in the same direction, moving, relative to the expansion, toward a specific region of the sky, in the general direction of the constellations Centaurus and Hydra, roughly in the southern part of the sky, including us. The Milky Way itself appears to be moving toward that same region. Not a little, not by the modest amount that the gravitational pull of the Virgo cluster would explain, by hundreds of kilometers per second, over and above everything else. Something is there, something in that direction, something massive enough to be pulling hundreds of galaxies across hundreds of millions of light years of space toward the same gravitational convergence, something that the universe has been quietly directing our motion toward for billions of years. And here is the part that makes this genuinely strange. A great deal of the mass doing the pulling cannot be seen at all, not because it is hidden behind dust, but because it does not emit light in the first place. This is dark matter, the invisible substance that makes up most of the mass of the universe, detectable only through its gravity. The same astronomer whose work on galaxy rotation curves provided some of the strongest early evidence for dark matter. Vera Rubin, after whom a major new observatory is now named, was part of the generation of researchers who established that the visible universe is only a fraction of what actually shapes cosmic motion. The flows that point toward the Great Attractor are flows through a gravitational landscape, sculpted largely by matter we cannot directly observe. Something that, when astronomers turn their telescopes toward that part of the sky, they cannot see, because it is hiding behind our own galaxy. The Milky Way's disk, the band of stars and dust and gas that forms our galaxy's plane, sits directly between us and the source of the pull. Like a wall between us and a window. The light from whatever is back there cannot get through, the dust absorbs it, the stars overwhelm it. The zone of avoidance, astronomers call it. The region of the sky where our own galaxy makes it effectively impossible to observe what lies beyond. The Milky Way is being pulled at over 600 kilometers per second towards something that nobody, for more than 20 years, could actually see. And the mystery would be named before it would be found. When astronomers first measured the motion, they could not explain it with anything known to exist in the direction the motion was pointing. The Great Attractor was named before it was found. Its effects were measured before its identity was known. And, when it was finally identified, after decades of struggling to see through the dust and gas of our own galaxy, the answer raised a question that is still being answered today, because the Great Attractor turned out to be the center of something vast, something we had been living inside without knowing it, and that something, it is now emerging, may itself be falling towards something even larger, the mystery behind the mystery behind the mystery. This video is about the Great Attractor. It is about the Milky Way, our entire galaxy, with its 200 to 400 billion stars, moving through space at approximately 630 kilometers per second relative to the cosmic microwave background, the reference frame of the universe's earliest light. Part of that motion is explained by the gravitational pull of nearby structures. But a significant component of that motion points toward a specific region of the southern sky, a region behind the Milky Way's own disk, that for most of the 20th century could not be observed directly. In 1988, a group of astronomers known as the Seven Samurai formally documented this anomalous flow and named its apparent source the Great Attractor. The name was evocative, slightly alarming, and technically accurate. Something in that direction was attracting galaxies, including ours. It took another 2 decades to fully understand what it was. In 2014, Brent Tully and colleagues at the University of Hawaii published a landmark paper defining the Laniakea supercluster, a vast basin of gravitational attraction containing approximately 100,000 galaxies, spanning roughly 500 million light-years, with the Great Attractor at its center. The Great Attractor, it turned out, was not a single extraordinary object. It was a place, the focal point of a supercluster we had been living inside without knowing it. In 2024, a team including Tully published updated findings suggesting that Laniakea itself may sit inside an even larger basin of attraction, centered on the Shapley concentration, several hundred million light-years away. That is roughly 10 times the volume of Laniakea. This is not a story about a single answer. This is about a sequence of nested revelations, each answer exposing a larger question, each solved mystery revealing a bigger mystery behind it, that has been unfolding in cosmology for 40 years and may not be finished yet. By the end of this video, you will understand exactly what the Great Attractor is, how it was discovered, what the Laniakea supercluster revealed about our cosmic address, and why the 2024 update means that even that answer may be only the beginning. So, what exactly is pulling our galaxy at over 600 kilometers per second? Why did it take 20 years after the Great Attractor was named for anyone to actually see what it was? What is the Laniakea supercluster, and what does it mean that we have been living inside it, without knowing it, for the entire history of our species? What is the Shapley concentration? And why do the most recent cosmological surveys suggest that even Laniakea may be falling toward it? Are we inside a structure 10 times larger than Laniakea, whose edges we haven't finished mapping? And what does any of this mean for our place in the universe, for where we are, and where everything around us is going? This is not a video about Earth being in danger. The Great Attractor is not going to swallow us. The motion of the Milky Way toward the Great Attractor region is a cosmic scale process, operating on timescales of tens of billions of years, and the expansion of the universe is simultaneously working to push structures apart on the largest scales, even as gravity pulls them together on smaller scales. We will never reach the Great Attractor. The expansion of the universe is carrying it away from us faster than gravity can pull us toward it. None of this threatens Earth. None of this threatens the solar system. None of this threatens anything on a human timescale. But this is also not a video that treats cosmic scale as merely academic. What we are talking about is the discovery that our entire civilization, every human who has ever lived, every star we can see in the night sky, every galaxy in every Hubble Deep Field image, is part of a structure so enormous that we are only now developing the instruments to understand its shape. We named the Great Attractor before we found it. We found Laniakea before we knew we lived in it, and the structure that may contain Laniakea is still being mapped. That is not nothing. That deserves a careful look. Stay with me. Quick pause. If these are the kinds of stories that pull you in, the grandest possible scale of cosmology told clearly and honestly, hit subscribe. Galaxy Pulse goes beyond the headlines every single time. Now, back to the Great Attractor, and to the moment a group of astronomers realized that something enormous was hiding behind our own galaxy. To understand what the Great Attractor is and why its discovery mattered, we need to understand 2 things. First, what galaxy motions can tell us. Why the velocity of a galaxy contains information about the gravitational environment it has been moving through. and how astronomers use those velocities to map the unseen structure of the universe. And second, what the zone of avoidance is. Why the Milky Way's own disk has been hiding one of the most massive structures in the local universe from our view for the entire history of astronomy. Both of those stories begin the same way, with astronomers noticing that galaxies were not moving the way they should. The universe is expanding. Edwin Hubble established this in 1929. By measuring the velocities and distances of a set of nearby galaxies and finding a clear proportional relationship between the two. The further away a galaxy, the faster it is moving away from us. Not because it is moving through space, at least, not entirely, but because the space between us and it is expanding. Every point in the universe is moving away from every other point, like raisins in a rising loaf of bread. The raisin bread image is worth holding onto, because it captures something genuinely counterintuitive about cosmic expansion. Imagine a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the point of view of any one raisin, all the others appear to be receding, and the more distant raisins recede faster, because there is more expanding dough between them. No raisin is at the center. The expansion looks the same from every raisin's perspective. That is exactly our situation in the universe. We are not at the center of the expansion. There is no center. Every galaxy sees every other galaxy receding, and the more distant ones recede faster, because there is more expanding space between us and them. The galaxies are not flying apart through space like debris from an explosion. The space between them is growing. The constant that describes this relationship, the rate at which recession velocity increases with distance, is called the Hubble constant. Its precise value has been a matter of debate for decades, and continues to be one of the most contentious measurements in cosmology. In fact, different methods of measuring it give persistently different answers, a discrepancy known as the Hubble tension, which is one of the deepest unresolved problems in the field. But the existence of the expansion itself is not in doubt. The universe is expanding, and Hubble's observations established the basic framework within which all of modern cosmology operates. In a perfectly uniform expanding universe, every galaxy's velocity would follow this relationship exactly. Measure the galaxy's distance, multiply by the Hubble constant. That is the galaxy's recession velocity. Clean, predictable, explained entirely by the expansion. The real universe is not perfectly uniform. Galaxies are not distributed randomly through space. They are clumped. They form groups and clusters, which are gravitationally bound structures in which galaxies orbit each other rather than expanding away from each other. Clusters are connected into larger filaments and sheets, with vast empty voids between them. The large-scale structure of the universe resembles, in 3 dimensions, an enormous cosmic web, sheets and filaments of matter surrounding bubbles of near emptiness that span hundreds of millions of light years. This cosmic web is one of the most important discoveries in modern cosmology, and it is worth understanding how it came to be. In the earliest moments after the Big Bang, the universe was almost perfectly uniform, a hot, dense plasma with only the tiniest variations in density from place to place. Variations of about 1 part in 100,000. Those tiny variations are visible today as the faint temperature fluctuations in the cosmic microwave background. But over billions of years, gravity amplified them. Regions that were slightly denser than average pulled in more matter, becoming denser still. Regions that were slightly emptier lost matter to their denser neighbors, becoming emptier still. The rich got richer, and the poor got poorer, gravitationally, until the smooth early universe had organized itself into the web of filaments and voids we see today. The galaxies form along the filaments, like droplets of water condensing along the strands of a spider's web. The clusters form at the nodes where filaments intersect, and the great voids, the empty bubbles, some of them hundreds of millions of light years across, are the regions that gave up their matter to the surrounding structure. This is the universe at the largest scales. Not a random scattering of galaxies, but an intricate, organized, evolving structure shaped entirely by gravity acting on those primordial density variations. In this clumped universe, gravity complicates the simple Hubble flow. A galaxy that sits near a massive cluster is gravitationally attracted to that cluster. That attraction pulls the galaxy, adding a component of motion that is not the expansion. A component that pushes the galaxy's measured velocity slightly above or below what the Hubble law alone would predict. Astronomers call this extra velocity the peculiar velocity. It is the component of a galaxy's observed motion that deviates from the pure Hubble flow. And peculiar velocities are extraordinarily useful because they contain information about the gravitational field the galaxy has been moving through. A galaxy moving faster than the Hubble flow in a specific direction has been pulled in that direction. Something massive is there. Something is attracting it. By measuring the peculiar velocities of many galaxies in a region of space, astronomers can map the gravitational landscape, identifying concentrations of mass, even in regions they cannot directly observe, by reading the imprint of those concentrations in the motions of the galaxies around them. Pause here for a moment, because this is the key insight that makes the Great Attractor story possible. The universe we can see is not the only universe that shapes our motion. The gravitational influence of structures we cannot see, because they are too far away, because they are behind dust clouds, because they are too dim to detect with current instruments, leaves a mark in the velocities of the galaxies we can see. Those velocities are a kind of message from the unseen universe. And learning to read that message is how cosmologists discovered the Great Attractor. There is a second piece of the story that needs to be in place before we can proceed. The cosmic microwave background. In the mid-1960s, Arno Penzias and Robert Wilson detected a faint radio signal coming uniformly from all directions of the sky. This signal was the thermal afterglow of the Big Bang. The radiation produced when the universe was approximately 380,000 years old and cooled enough for neutral atoms to form, released from the primordial plasma and traveling through space ever since. The cosmic microwave background fills the universe. It is extraordinarily uniform, the same temperature in every direction to about 1 part in 100,000. This uniformity makes it uniquely valuable as a reference frame. If the Milky Way is moving relative to the CMB, if the CMB appears slightly hotter in one direction and slightly cooler in the opposite direction due to our own Doppler motion, then we can measure the absolute velocity of our galaxy relative to the universe's global rest frame. When this measurement was made and refined in the 1970s and 80s, the answer was striking. The Milky Way is moving at approximately 630 kilometers per second relative to the CMB rest frame. That is roughly 2 million kilometers per hour, well over 1 million miles per hour. It is worth pausing on what this measurement actually represents, because it is one of the most remarkable facts about our cosmic situation. The cosmic microwave background is the closest thing the universe has to a fixed reference frame, the average rest frame of all the matter in the observable universe, the frame in which the Big Bang's afterglow looks the same in every direction. When we measure our motion relative to it, we are measuring our absolute velocity through the universe in the most meaningful sense available. And that velocity is enormous. The entire Milky Way, with its hundreds of billions of stars, our sun and our solar system and our planet and everyone on it, is hurtling through the universe at 630 kilometers per second, a speed at which you could cross the entire diameter of the Earth in about 20 seconds. We do not feel it. There is no sensation of motion, no wind, no resistance, because everything around us, the entire galaxy, is moving together, and because space itself provides no fixed landmarks against which to feel our speed. But the motion is real, and it is measurable, written into the faint temperature pattern of the oldest light in the universe. It is one of the fastest sustained motions of any large gravitational system that has been directly measured, and it is not random. It is directed toward a specific region of the sky, in the direction of the constellations Centaurus and Hydra, roughly behind the disk of our own galaxy. Something is pulling us there, under the standard model of the expanding universe. Here is what the motion of the Milky Way should look like. It should participate in the Hubble flow, moving away from distant galaxies in proportion to the expansion. It should have a modest additional motion toward the Virgo cluster, the nearest major mass concentration to our local group, and there should be relatively small random motions beyond that. The kind of gentle gravitational jostling you would expect from living in a universe with the density and distribution of matter that observations suggest. What the CMB measurements showed was different in magnitude. 630 kilometers per second is not a modest motion. It is a large, directed, sustained pull toward a specific region of the sky. And the Virgo cluster, while real and while contributing to the motion, was nowhere near massive enough to account for all of it. Even combined with all other known mass concentrations in the local universe visible at the time, the accounting did not work. Something was missing from the inventory of the local universe. Something massive, somewhere in the general direction of the southern sky, that was pulling the Milky Way and every other nearby galaxy toward it at hundreds of kilometers per second. The problem was that nobody could see it. The region of sky toward which the motion pointed was behind the zone of avoidance, the strip of sky running along the Milky Way's galactic plane, where the dust and gas of our own galaxy's disk absorbs the light of anything beyond it. In optical wavelengths, this band is essentially opaque. Whatever massive structure existed in that direction was invisible to every optical telescope of the era. We were being pulled towards something we could not look at. And the gap between what the standard model predicted for our motion and what the measurements actually showed, that gap was large enough and robust enough that it could not be explained by measurement error or by structures already known. Something was there, something enormous, and it was hiding behind our own galaxy. The formal discovery of the Great Attractor was not the work of a single astronomer or a single moment of insight. It was the product of years of collaborative work by a group of 7 researchers who, beginning in the early 1980s, pooled their expertise and their data to tackle a problem that no individual group had the resources to solve alone. The group coalesced informally, meeting periodically to go through data together over long working sessions. They came to be called the 7 Samurai, a nickname that stuck, partly because there were 7 of them, partly because the work they were doing felt, in some sense, like a battle against the limits of what could be known from the available data. The 7 were Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Donald Lyndon Bell, Roberto Turlevich, and Gary Wegner. Stellar astronomers and cosmologists from universities and observatories in the United States, the United Kingdom, and elsewhere. What bound them was a shared interest in one of the most useful distance indicators available to observational cosmology at the time. A relationship sometimes associated with the work of Faber and Robert Jackson, connecting the brightness of an elliptical galaxy to the motions of the stars within it. The principle is this: for an elliptical galaxy, there is a correlation between the galaxy's true luminosity and the velocity dispersion of its stars. the typical speeds at which stars within the galaxy move relative to each other, measurable from the width of spectral lines. More luminous, elliptical galaxies have higher velocity dispersions. The correlation is tight enough that, by measuring a galaxy's velocity dispersion, you can infer its true luminosity, and from there its distance. Distance, combined with measured recession velocity, gives you the peculiar velocity. The Seven Samurai applied this technique to hundreds of elliptical galaxies spread across a large region of the sky. It was painstaking work. Each galaxy required careful spectroscopic observation and analysis. The data accumulated over years, and when it was assembled and analyzed, the result was unambiguous. There was a large-scale coherent flow. It is worth appreciating just how much careful work this represented, and how easy it would have been to get wrong. Measuring a peculiar velocity requires measuring two things independently: the galaxy's distance and its recession velocity. The recession velocity is relatively easy. You measure the redshift of the galaxy's light. But the distance is hard. You cannot simply measure how far away a galaxy is. You have to infer it from some property of the galaxy that correlates with its true brightness, and every such method carries uncertainties. The peculiar velocity is then the small difference between the velocity you would expect from the distance and the velocity you actually observe. It is a difference between two larger, uncertain numbers, exactly the kind of measurement that is vulnerable to systematic error. The Seven Samurai understood this, part of why there were 7 of them, pooling their data and checking each other's work, was precisely to guard against the possibility that the flow they were seeing was an artifact of measurement error, rather than a real feature of the universe. When 7 careful researchers, using a well-understood distance indicator, applied to hundreds of galaxies, all converge on the same conclusion, the result carries weight that no single measurement could. Hundreds of galaxies, spread across a region spanning hundreds of millions of light-years, were all moving with a systematic component of velocity in the same direction. Not randomly, not in small groups locally. Coherently, across the entire surveyed volume, toward a region in the southern sky that sat behind the zone of avoidance. The Seven Samurai published their formal analysis in 1988 in the Astrophysical Journal, in a paper describing a large-scale streaming motion in the local universe. The paper described the flow, characterized its magnitude and direction, and estimated the mass required to produce it. Donald Lynden-Bell gave the source of the flow its name, the Great Attractor. It was a name that captured something essential about the discovery, not just a mass concentration. An attractor, something that the entire surrounding universe, on a vast scale, was flowing toward. Something that, in the gravitational topography of the local universe, represented a deep valley toward which every nearby galaxy was slowly descending. And it was great, large, dominant, unlike any structure previously identified. But the Great Attractor was also, at the moment of its naming, invisible. The Zone of Avoidance covered the region where it sat. Optical surveys could not penetrate it. The Great Attractor was inferred entirely from its gravitational effects on the galaxies around it. It was a shadow cast by a hidden object, measurable, real, but without a visible source. The search for the source, the decade-long effort to see what was actually behind the Zone of Avoidance, would become one of the defining projects of observational cosmology in the 1990s. Before we follow the search for the Great Attractor's identity, let us make sure the underlying concepts are clear, because the rest of this story depends on understanding a few things that are, once explained, not difficult, but that most popular coverage of the Great Attractor leaves as assumed background. Think of it this way. Imagine you are a ball rolling on a large, complicated landscape. The landscape has hills and valleys, rises and drops. From where you sit, you cannot see most of it. You can only see what is immediately around you, but you can feel which way you are rolling. If you are rolling consistently in one direction, not randomly, not in circles, but consistently toward a specific point, you know there is a valley in that direction, something lower, something that gravity is pulling you toward, even though you cannot see it directly. That is exactly what the peculiar velocity measurements were doing. The galaxies in the local universe are the balls, the gravitational landscape of the universe, shaped by the distribution of mass, including dark matter that cannot be directly observed, is the hills and valleys. By measuring which way the galaxies are rolling, astronomers can infer the shape of the landscape, including the location of gravitational valleys that might be hidden behind dust or simply too far away to observe directly. Three concepts are essential to follow the rest of this story clearly. The first is peculiar velocity itself. Every galaxy in the universe has two components of motion. One is the Hubble expansion, the recession from all other galaxies due to the expansion of space. This component depends only on distance. More distant galaxies recede faster. The second component is the peculiar velocity, everything else, the gravitational push and pull of nearby structures, the infall toward massive clusters, the coherent flows driven by large-scale mass concentrations like the Great Attractor. Peculiar velocities are typically small compared to the Hubble recession at large distances, but in the local universe, where the Hubble recession is modest, peculiar velocities can be a significant fraction of the total observed velocity, large enough to be measured, significant enough to tell us something about the gravitational environment. The second concept is the zone of avoidance. The Milky Way is a disk galaxy. We live inside the disk. When we look out along the plane of the disk, the band of the Milky Way stretching across the night sky, we are looking through the maximum thickness of dust and gas the galaxy contains. That dust absorbs optical light. Background galaxies that sit behind this dust, in the direction of the galactic plane, are obscured. Some are hidden entirely. Others are detectable only at wavelengths, infrared, radio, X-ray, that penetrate the dust more effectively than visible light. The Great Attractor sits almost directly behind this band, in the zone of avoidance. For optical astronomers in the 1980s and 90s, this was deeply frustrating. The most interesting structure in the local universe was hiding behind the most observationally challenging region of the sky. The third concept is what the Great Attractor actually is, not a single object, but a gravitational focal point. This is perhaps the most important concept to understand, and it is the one most often misrepresented in popular coverage. The Great Attractor is not a giant black hole. It is not a single massive galaxy. It is not a compact, extraordinarily dense object. It is a region, a place in space where the collective gravitational pull of many galaxy clusters converges, producing a deep valley in the gravitational landscape of the local universe, toward which surrounding galaxies flow. It is more like a drain than a stone. The drain is not itself doing anything unusual. It is simply the place where the water collects. The water, the galaxies, flows toward it because of the shape of the basin around it. And the basin, it would eventually turn out, was vast beyond anything the seven samurai had imagined when they named what they had found. So here is where the stakes start to rise. If the Great Attractor is real, and by the early 1990s, it was clear beyond reasonable doubt that something genuinely unusual was going on in the Centaurus Hydra region, then our understanding of our place in the universe needed to be updated. The Milky Way was not just a galaxy among galaxies, participating in the random gravitational give and take of a well-mixed universe. It was a galaxy participating in a large-scale coherent flow, being pulled by something vast, across a trajectory that had been established billions of years ago and would continue for billions more. The motion is not dangerous. The Great Attractor is far enough away, and the approach slow enough on cosmic timescales, that its gravitational effects on the solar system are completely negligible. This needs to be said plainly, because the name creates the impression of something threatening. But the cosmological implications were genuinely significant. The existence of the Great Attractor implied a mass concentration larger than anything previously known in the local universe. To produce the flow velocities observed over the region the seven samurai had surveyed, hundreds of kilometers per second, coherent across hundreds of millions of light years, required a concentration of mass on the order of 10 to the 16th solar masses. That is a number so large it barely has meaning on a human scale. 10,000 trillion times the mass of our Sun, in a region of space whose full extent remained unknown. It challenged models of large-scale structure formation. How had such a large concentration assembled in the time available since the Big Bang? What did the existence of the Great Attractor tell us about the cosmological parameters, the density of matter, the density of dark energy, the geometry of spacetime, that governed how the universe built its large-scale structure? These were not trivial questions. They were connected to the most fundamental measurements in cosmology, and they could not be answered until the Great Attractor could actually be seen. For 15 years after the Great Attractor was named, it remained a mystery behind a wall. X-ray and radio observations gave partial views. Individual galaxy clusters were identified in the general region. The Norma cluster, a dense, rich concentration of galaxies at approximately 220 million light-years, one of the most massive structures in the local universe, emerged as a candidate for the center of the Great Attractor. The Norma cluster is worth dwelling on, because it represents the moment the Great Attractor began to acquire a face. For years, the Great Attractor had been a pure abstraction, a direction in the sky, a gravitational pull, a number in a velocity catalog. But the Norma cluster is a real, observable object. A rich galaxy cluster, comparable in mass to some of the most massive clusters known, sitting almost exactly where the gravitational analysis said the center of the attraction should be. When astronomers first managed to characterize it through the Zone of Avoidance, they were, in a sense, finally seeing a piece of the thing that had been pulling on us all along. Not the whole Great Attractor, which, as we now understand, is a distributed gravitational basin rather than a single object, but its densest, most prominent component. The abstraction had a concrete center at last, but the complete picture remained out of reach. The Zone of Avoidance was still blocking the view. The mass accounting still did not add up cleanly. And the relationship between the Great Attractor and the structures visible beyond it, in particular, a vast galaxy supercluster known as the Shapley concentration, remained unclear, until a set of new surveys, using wavelengths of light that could pierce what the optical telescopes could not, began to reveal what had been hidden. The effort to see through the Zone of Avoidance was one of the defining observational challenges of cosmology in the 1990s. The problem was not a simple one of increasing telescope sensitivity. The Zone of Avoidance is not just difficult, it is physically opaque to visible light. The dust in the galactic plane absorbs photons at optical wavelengths with near total efficiency in the densest regions. No optical telescope, regardless of its light collecting area, can see a background galaxy through the thickest parts of the Milky Way's disk. The problem required a different approach. The solution came from three directions simultaneously. The first was X-ray astronomy. Galaxy clusters contain hot intracluster gas, plasma, at temperatures of tens of millions of degrees, emitting X-rays copiously. X-rays, at the energies relevant for cluster detection, are less affected by galactic dust absorption than optical light. The ROSAT satellite, a German-led X-ray telescope that operated through much of the 1990s, surveyed the entire sky, including the Zone of Avoidance, and produced catalogs of galaxy clusters detected through the Milky Way's disk. The ROSAT surveys revealed a rich galaxy cluster environment in the Great Attractor region. The Norma cluster, already suspected as the center of the Great Attractor, was confirmed as one of the most massive clusters in the local universe. Other clusters and groups were identified in the surrounding region. The picture began to take shape. The second approach was radio astronomy. Neutral hydrogen atoms emit radio waves at a specific wavelength, 21 centimeters. This wavelength passes through galactic dust almost unimpeded. The Parkes telescope in Australia and other radio observatories conducted systematic 21-centimeter surveys of the Zone of Avoidance, detecting galaxies by their hydrogen emission rather than their starlight. René Kronkortueg, an astronomer who has specialized in surveying the Zone of Avoidance, led some of the most systematic of these surveys, cataloging many previously unknown galaxies hiding behind the galactic plane. What the hydrogen surveys revealed was an extraordinarily rich galaxy environment in the Great Attractor region, not just the Norma cluster, but a surrounding concentration of galaxy clusters extending across hundreds of millions of light years, sometimes called the Hydra Centaurus supercluster, of which the Norma cluster is the most prominent concentration. The third approach was near-infrared astronomy. Stars, unlike dust clouds, emit strongly in the near-infrared, and near-infrared light penetrates dust far better than optical light. The 2-micron all-sky survey, known as 2MASS, conducted a complete near-infrared survey of the entire sky, including the Zone of Avoidance, and detected galaxies through the galactic plane that were invisible in optical surveys. The 2MASS data, when analyzed in the Great Attractor region, confirmed the presence of a massive galaxy concentration centered on the Norma cluster. By the early 2000s, the picture had come together. The Great Attractor was real. It was centered on the Norma cluster and the surrounding Hydra Centaurus concentration. It was a mass concentration of the rough magnitude the Seven Samurai had estimated, and the flow toward it, the coherent motion of many galaxies, including our own, in its direction, was real and well characterized. But there was a problem with the mass accounting. Even with the Norma cluster and the full extent of the Hydra Centaurus region included in the mass budget, the gravitational attraction appeared insufficient to fully explain the observed peculiar velocities. Something beyond the Zone of Avoidance, something at a greater distance, was contributing to the flow, and that something was the Shapley concentration, well beyond the Great Attractor region. The Shapley supercluster, one of the richest concentrations of galaxy clusters in the nearby universe, was exerting a gravitational pull on the entire local universe. Not a dominant pull at the distances involved, but a measurable one. A contribution to the peculiar velocity field that had to be accounted for. The question was whether the Great Attractor and the Shapley concentration were two separate features in the local gravitational landscape, or whether they were connected as parts of a single, larger structure. That question would take another decade to seriously address. And when it was addressed, the answer redefined our cosmic address. In September of 2014, a paper appeared in the journal Nature. The title was The Laniakea Supercluster of Galaxies. The lead author was R. Brent Tully, an astronomer at the University of Hawaii Institute for Astronomy, who had spent much of his career developing the tools to measure galaxy distances with precision sufficient to map the large-scale peculiar velocity field. His co-authors were Helene Courtois, Yehuda Hoffman, and Daniel Pomerd. The paper was immediately recognized as a landmark. It did not describe a new detection or a new observation in the ordinary sense. It described a new way of defining what a supercluster is, and in applying that definition to the best available data on galaxy motions in the local universe. It revealed that the Milky Way, the local group, the Virgo cluster, and approximately 100,000 other galaxies all lived inside a single, coherent gravitational structure that nobody had previously mapped as a whole. They named it Laniakea. The word is Hawaiian, Lani, meaning heaven or sky, and Akea, meaning spacious or immeasurable, immense heaven. The name was suggested by a Hawaiian language scholar, and once you understood the scale of the structure being described, it seemed exactly right. To understand what Tully's team actually did, and why the concept of Laniakea was a genuine scientific advance rather than simply a rebranding of known structures, you need to understand the distinction between two ways of defining a supercluster. The traditional definition of a supercluster was based on galaxy density. A supercluster was a region of space where galaxies were more tightly concentrated than average. By this definition, the local supercluster, the Virgo supercluster, had been known since the 1950s and 60s. It was the cluster of galaxy clusters centered on the Virgo cluster. Our local group was a peripheral member of it. The problem with density-based definitions is that they are arbitrary. How much denser than average does a region have to be before it counts as a supercluster? The density threshold is a human decision, not a physical boundary. Tully's team used a different definition, one based on gravitational dynamics rather than density. They defined a supercluster as a gravitational watershed, a region of space from which all matter flows toward a common center, rather than flowing away toward some other structure. Think of it like water on a landscape. A watershed is a region of land from which all rainfall drains toward the same river or body of water, rather than flowing over a ridge into another drainage basin. The boundaries of a watershed are defined by the ridges, the high points in the landscape where the flow direction changes, not by how densely it rains. This is a genuinely powerful idea, and it is worth understanding why it represents such an advance over the old density-based definition. On Earth, you can define a watershed precisely and objectively. Every drop of rain that falls on one side of a mountain ridge flows, eventually, into one river system. Every drop on the other side flows into a different one. The boundary between the two is not arbitrary, it is determined by the physical shape of the land. You do not have to choose a threshold or make a judgment call. The landscape itself defines the boundary. The same logic, applied to the universe, gives superclusters an objective definition for the first time. Instead of asking, how densely packed are the galaxies here? A question with no natural answer, you ask, where do these galaxies flow? Every galaxy, under the influence of all the mass around it, is drifting in some direction. Map enough of those drift directions, and you can identify the surfaces where the flow direction reverses. The cosmic ridges that separate one gravitational drainage basin from another. A supercluster, in this definition, is everything that drains toward the same place. The cosmological equivalent of a ridge is a surface of gravitational divergence, a location in space where galaxies on one side are flowing toward one attractor, and galaxies on the other side are flowing toward a different attractor. By mapping these divergent surfaces in the local universe, using a catalog of galaxy distances and peculiar velocities, Tully's team could define superclusters as gravitational basins with objectively defined boundaries. When they applied this method to the local universe, the result was striking. The Milky Way sat inside a gravitational basin roughly 500 million light-years across. The flow lines, the paths along which galaxies were moving in the local universe, under the influence of all the mass concentrations around them, all converged toward a single region, the Great Attractor, the focal point of the Norma cluster and the surrounding Hydra Centaurus concentrations. That basin was Laniakea. It contained approximately 100,000 galaxies, with a total mass on the order of 10 to the 17th solar masses. And the Milky Way was not at its center, not even particularly close to it. It sat in the outer regions, a small galaxy in a large structure, with 100,000 galactic neighbors in the same gravitational basin, all slowly flowing toward the same center. The Virgo supercluster, our previously understood home supercluster, turned out to be just a small part of Laniakea, a substructure in a much larger whole. Like thinking you lived in a village, only to find that the village was a neighborhood in a city you had never been able to see clearly enough to map. The implications for our cosmic address were immediate and profound. We had always been in Laniakea. The supercluster was not new. The galaxies it contained had always been there. The gravitational flows that defined its boundaries had been operating for billions of years. What was new was our ability to see it as a whole, to map the flow lines, identify the drainage basin boundaries, and recognize that 100,000 galaxies, including our own, shared a common gravitational fate. All of us, the Milky Way, the Andromeda Galaxy, the Virgo cluster, the 100,000 other galaxies of Laniakea, are slowly being drawn toward the Great Attractor region, moving at hundreds of kilometers per second across timescales that make geological time seem brief. We will never reach it. The expansion of the universe is accelerating, driven by dark energy, and on the timescales relevant to the flow, tens of billions of years. Dark energy will eventually overcome the gravitational pull and begin carrying the outer regions of Laniakea away from its center. Laniakea, as a coherent gravitational structure, is temporary. It is assembling now, but it will not remain assembled forever. This is one of the strangest and most beautiful facts in all of cosmology, and it deserves to be sat with rather than rushed past. We are moving toward the Great Attractor at 630 kilometers per second. That is a real, enormous, sustained motion, and yet we will never arrive. The reason is dark energy, the mysterious component of the universe, discovered in the late 1990s, that is causing the expansion of space to accelerate rather than slow down. As space expands faster and faster, the distance between us and the Great Attractor region grows. Gravity pulls us toward it. The expansion of space carries it away from us, and over cosmic time, the expansion wins. So our situation is genuinely paradoxical. We are falling toward a destination that is receding faster than we can approach it. We are passengers on a journey that has a direction but no arrival. The Great Attractor is not a place we are going to. It is a place we are oriented toward, a gravitational true north that defines the shape of our local universe, but that we are physically incapable of reaching. The universe set us in motion toward it billions of years ago, and the same universe, through dark energy, has guaranteed that we will never get there. But for now, we are in it. And for the first time, we knew it. The 2014 Laniakea paper seemed, to many readers, like a final answer. The Great Attractor had a name, it had a structure, it had a context. Not an isolated anomaly, but the center of a vast supercluster, the focal point of 100,000 galaxies flowing toward a common basin. The mystery that the Seven Samurai had named in 1988, that had resisted explanation for a quarter century, had been resolved. But the 2014 paper contained a quiet note that most coverage missed. Laniakea was not isolated. The flows at the edges of Laniakea, the motions of galaxies at the supercluster's periphery, showed evidence of external influence. Something beyond Laniakea's boundaries was contributing to the peculiar velocity field. Something at greater distances, more massive still, was pulling. That something was the Shapley concentration. Harlow Shapley, the American astronomer who had famously argued, correctly, that the Sun was not at the center of the Milky Way, had noticed, in the 1930s, that there was an unusual concentration of galaxies in the direction of the constellation Centaurus, at a distance then difficult to measure but clearly far greater than the local clusters he was studying. He catalogued it and moved on. For decades, it sat in the literature as an interesting but poorly characterized distant feature. By the 1980s and 90s, as large-scale redshift surveys mapped the distribution of galaxies out to greater distances, the Shapley concentration had been characterized in more detail. It was one of the richest concentrations of galaxy clusters in the observable universe. Its total mass was enormous, comparable to or exceeding the mass of the entire Laniakea supercluster, concentrated in a region roughly 650 million light-years from the Milky Way. To put the Shapley concentration in perspective, it is the single largest concentration of mass in the nearby universe. It contains many rich galaxy clusters, each of which contains hundreds or thousands of galaxies, all packed into a region far denser than the cosmic average. If the Great Attractor region represents a substantial gravitational valley, the Shapley concentration represents something deeper still, a more massive accumulation, farther away, exerting its pull across an even greater volume of space. The fact that it lies in roughly the same direction as the Great Attractor, just much farther out, is part of what made the two so difficult to disentangle. From our vantage point, the nearby pull of the Great Attractor and the more distant pull of Shapley point much the same way across the sky. At that distance, its gravitational influence on our local universe was modest but measurable. Several analyses through the 1990s and 2000s had argued that Shapley was contributing to the local peculiar velocity field, that some fraction of the Milky Way's motion was actually driven not by Laniakea's own internal dynamics, but by Shapley pulling from beyond. The question was whether this was a secondary effect, Shapley nudging Laniakea's dynamics slightly, or whether it was something more fundamental. Whether the boundary of Laniakea, as defined by the gravitational watershed method, was the true boundary of our cosmic home, or whether Laniakea itself was falling into a larger basin. In 2023, work using the cosmic flows for catalog, the most comprehensive compilation of galaxy distances and peculiar velocities yet assembled, incorporating roughly 56,000 galaxy distance measurements, applied the watershed methodology to the local universe in greater detail. It defined the major basins of attraction within roughly 1 billion light-years and confirmed Laniakea's extent while identifying its neighboring structures. And it found something that pushed the question further. The flow lines at the edge of Laniakea were not simply flowing inward toward the Great Attractor. There appeared to be a component of motion, collectively, toward the Shapley concentration. The question of whether Laniakea as a whole was drifting toward Shapley, and whether it should properly be regarded as a sub-basin of a larger Shapley-centered structure, moved from speculation to active analysis. In 2024, a paper led by Aurélien Valade, with co-authors including Brent Tully, Daniel Pommard, Yehuda Hoffman, Noam Libeskind, and others, was published in Nature Astronomy under the title, Identification of Basins of Attraction in the Local Universe. It applied an advanced reconstruction algorithm to the cosmic flows for data to map the gravitational basins of the local universe probabilistically. The result, widely reported, was striking. The analysis indicated roughly a 60% probability that the Milky Way belongs to a gravitational basin centered not on the Great Attractor but on the Shapley concentration, a basin roughly 10 times larger in volume than Laniakea. If confirmed, This would mean the original Laniakea is a sub-basin within something much grander, similar to how the Virgo supercluster turned out to be a smaller piece of Laniakea. Our cosmic address would need another line. There is an important detail here that popular coverage of the 2024 result often left out. The Shapley Basin was not even the largest structure the analysis identified. The same study found that the largest basin of attraction in the surveyed volume was associated with the Sloan Great Wall, a structure more than twice the volume of the Shapley Basin. The local universe, mapped this way, contains several enormous basins, and our membership in any one of them is, at the current level of data, a matter of probability rather than certainty. The challenge is that the current cosmic surveys may not yet cover enough of the universe to map these immense basins completely. As one of the co-authors, Asin Kuokshi, put it, the cosmic surveys may not yet be large enough to map the full extent of these immense basins. The galaxy distance catalog needed to define the boundary of a Shapley-centered basin reliably is larger than what currently exists. Building it requires more observations at greater distances with greater precision than the cosmic flows for catalog provides. Several major ongoing and planned surveys are expected to fill this gap within the next decade. The Dark Energy Spectroscopic Instrument, DESI, is collecting spectra of tens of millions of galaxies and will produce distance catalogs far richer than those available today. The Vera Rubin Observatory's Legacy Survey of Space and Time will provide photometric data on billions of galaxies, enabling new approaches to distance measurement at scales that were previously inaccessible. When these surveys are completed and their data incorporated into peculiar velocity analyses, the question of whether Laniakea is a sub-basin of a Shapley-centered structure will, in all likelihood, be answered. But, in the meantime, we live in the uncertainty. We know we are in Laniakea. We know we are moving toward the Great Attractor region. And we know, with roughly 60% probability, that Laniakea is itself falling into something much larger. The nested basin pattern, local group within the Virgo cluster's sphere of influence, the Virgo supercluster as part of Laniakea, possibly part of a Shapley-centered basin, is one of the most vertiginous facts in modern cosmology. Every time we think we have found the boundary of the structure we live in, the boundary turns out to be a sub-boundary within something larger. The story has always been the same story. We just keep discovering we are telling it at the wrong scale. There are three ways to interpret what the Great Attractor, Laniakea, and the emerging Shapley picture tell us about our place in the universe. They sit on a ladder, conservative at the bottom, bold at the top. Each one is held by researchers working at the frontier of large-scale structure cosmology. Each one has supporting evidence, and the choice between them will be made, not by debate, but by data. As the next generation of galaxy surveys fills in the picture, the conservative interpretation is that Laniakea is well-defined, the Great Attractor is explained, and Shapley's influence is real but secondary. In this view, the 2014 definition of Laniakea is robust. The gravitational basin is well characterized. The flow lines converge on the Great Attractor. Shapley exerts a gravitational influence on Laniakea's dynamics, but not enough to redefine the boundary of our home supercluster. Laniakea remains our cosmic home, and the Great Attractor at its center remains the primary gravitational focal point for our region of the universe. The supporting evidence for this view is the extensive cosmic flows dataset and the mathematical robustness of the watershed boundary definition. When the calculation is done with the available data, Laniakea's boundaries are clear. The weakness of this view is that the 2024 analysis explicitly reports a 60% probability that the Milky Way belongs to a larger basin. The conservative view requires that the additional data, when it comes, will show the Shapley contribution is insufficient to define a larger basin. The moderate interpretation is that Laniakea is a sub-basin, and the Shapley Basin is our true cosmic home. In this view, the 2024 result points the right way. The pattern that is played out at every previous scale. The Virgo supercluster was a sub-feature of Laniakea. Laniakea may be a sub-feature of a Shapley Basin, repeats at the next level. Our cosmic address needs another line, not the Virgo supercluster, not Laniakea, but the larger structure centered on Shapley, which contains Laniakea as a sub-basin, in the same way that Laniakea contains the Virgo supercluster. The supporting evidence is the 60% probability from the 2024 analysis. The cosmic flows for indication that galaxy flows at Laniakea's periphery have a Shapley-directed component, and the historical pattern of each new survey revealing a larger enclosing structure. The weakness is that the full dataset needed to confirm the Shapley Basin does not yet exist. The 2024 analysis is a probabilistic inference from available data. The confirmation requires Dacey and Rubin scale surveys that are still being assembled. The bold interpretation is that the nested hierarchy of attractors may continue beyond Shapley, that there is always a larger structure, and the full picture of our cosmic location remains beyond current instrumentation. In this view, the pattern of nested basins is a fundamental feature of how the cosmic web is organized. Local group, to the Virgo cluster, to Laniakea, to the Shapley Basin, to perhaps the Sloan Great Wall Basin, and beyond. At some scale, dark energy wins and the hierarchy terminates, but that scale may be larger than what we can currently map. The fact that the 2024 analysis found the Sloan Great Wall Basin to be even larger than the Shapley Basin is, in this view, a hint that we have not yet found the top of the hierarchy. This view is more philosophical observation than testable hypothesis in the near term, but it is grounded in the mathematics of hierarchical structure formation, and it captures something real about the limits of what any generation of astronomers can know. Here is what is worth saying before we move to the implications. The Great Attractor story is, in a specific way, the story of how we learned to read our address. Think about how a cosmic address works: Earth, solar system, Milky Way galaxy, local group, Virgo cluster, Laniakea supercluster, possibly the Shapley Basin. Each of these is a real structure, defined by the gravitational organization of matter at a specific scale. And each of them was discovered only when we developed the tools to see at the relevant scale. We did not know we lived in a solar system until we had telescopes good enough to map the planets. We did not know we lived in a galaxy until we had instruments good enough to resolve it. We did not know about the local group until Edwin Hubble measured the distance to the Andromeda galaxy. We did not know about the Virgo supercluster until the mid-20th century. We did not know about Laniakea until 2014. At each stage, the discovery of the next structure up in the hierarchy was not a surprise that overturned previous knowledge. It was a revelation of a context that had always existed but had been beyond the reach of previous instruments. We have been inside Laniakea the entire time. We were always being drawn toward the Great Attractor region. We just did not know it until we developed tools to read the motions of thousands of galaxies and interpret them as a coherent flow. And the story is not finished yet. The Great Attractor was named before it was found. Laniakea was discovered before we knew we lived inside it. The Shapley Basin is being inferred before it is confirmed. And beyond the Shapley Basin, there may be more, or there may be the boundary where dark energy wins and the hierarchy ends. We do not know yet which it is, but we are close. Here is the strange thing about how the Great Attractor has been covered in popular media. The story tends to come in two forms, and neither one tells the complete picture. The first form is the alarming version, articles and videos that emphasize the motion, 2 million kilometers per hour, a mysterious force pulling us through space, the Great Attractor looming in the southern sky. This version is not technically wrong. The motion is real, the speed is real, the direction is real, but it is framed in a way that implies danger, or at least drama, that the underlying science does not support. The Milky Way is not in danger. Nothing is bearing down on us. The Great Attractor is not a threat. It is a place we are slowly moving toward on a timescale that makes the age of the universe seem brief. The alarming framing sacrifices accuracy for excitement. The second form is the educational explainer. The Great Attractor is Laniakia's center. Here is how superclusters form. These are more accurate, but they often stop at 2014, the Laniakea paper, and treat it as the final word. Most do not cover the 2024 update, suggesting a larger Shapley basin. Most do not explain the Zone of Avoidance story. Most do not tell you that we will never reach the Great Attractor, and almost none of them convey the emotional core of the story. The specific feeling of discovering that you have always been inside something vast that you didn't know was there. Here are specific things that popular coverage has consistently missed. The Zone of Avoidance story is almost entirely absent. The fact that our own galaxy's disk was hiding the Great Attractor for the entire history of modern astronomy, that the answer to one of the biggest questions in cosmology was literally behind our galaxy's own dust, is one of the most remarkable ironies in the history of science. The frustration of the researchers who knew something was there but couldn't look at it directly. The decade-long effort to find wavelengths that could pierce the obstruction. The moment the surveys revealed what had been hiding. This story has enormous dramatic and scientific interest, and it is almost entirely absent from popular coverage. The distinction between the Great Attractor as a phenomenon and as a place is rarely explained clearly. Most coverage either implies it is a specific massive object, a super black hole, a super galaxy, or it is so vague about what it actually is that viewers leave without understanding. It is neither. It is a gravitational focal point, a drain in the cosmic landscape, the place where the flow lines converge. This distinction matters because it changes how you think about our motion. We are not being pulled toward a specific massive object. We are falling down a gravitational slope whose low point happens to be in the Centaurus Hydra region. The 2024 update is almost entirely absent from popular science coverage. The finding that there is a 60% probability that Laniakea sits inside a larger Shapley-centered basin, and that the Sloan Great Wall Basin may be larger still, is one of the most significant recent developments in our understanding of the local large-scale structure. It changes our understanding of our cosmic address. This finding has not entered the popular science discourse in any meaningful way. The fact that we will never reach the Great Attractor is often omitted, and when it is included, it is treated as anticlimactic. It is not anticlimactic. It is one of the most profound and strange consequences of dark energy. We are moving towards something that the expansion of the universe is simultaneously carrying away from us. We are passengers on a trajectory whose destination is receding faster than we can approach it. The universe has set us on a course towards something we cannot reach. That is not disappointing. That is philosophically extraordinary. And there is something that almost no coverage engages with at all. The question of what it means, emotionally and philosophically, to know that you live inside a structure so large that light would take hundreds of millions of years to cross it, that every civilization that might ever have existed or will exist in this region of the universe shares the same gravitational home, that we discovered this not by traveling, not by building a telescope large enough to image the whole structure, but by reading the motions of galaxies and interpreting those motions as a convergent flow. That is how you discover the room you live in when the room is hundreds of millions of light-years across. You watch which way the water flows. In the years since the 2014 Laniakea paper and the 2024 update, the data that will eventually confirm or revise the Shapley Basin picture is being assembled. The first major development is DAISY. The Dark Energy Spectroscopic Instrument is a fiber-optic spectrograph mounted on a 4-meter telescope at Kitt Peak National Observatory in Arizona. It can measure the spectra of thousands of galaxies simultaneously, collecting redshifts and thus recession velocities at a rate that dwarfs any previous spectroscopic survey. Over its multi-year program, DAISY is collecting spectra of tens of millions of galaxies. For large-scale structure cosmology, this is transformative. The peculiar velocity field can only be determined accurately if you know both a galaxy's distance, independent of its recession velocity, and its recession velocity. DAISY provides recession velocities at unprecedented scale. Combined with independent distance measurements, the DAISY data will allow the peculiar velocity field to be mapped to distances far beyond what current catalogs achieve. This means the gravitational watershed boundaries in the local universe, including the possible boundary of a Shapley-centered superbasin, can be determined with far greater precision than the current probabilistic estimate. The second major development is the Vera Rubin Observatory. The Rubin Observatory's legacy survey of space and time, which is imaging the entire southern sky repeatedly in multiple wavelengths, will detect billions of galaxies and produce one of the deepest, most complete photometric surveys of the sky ever assembled. For large-scale structure studies, it provides photometric redshifts, rough distance estimates derived from the color of a galaxy, for enormous numbers of objects, and high-precision measurements of galaxy shapes that enable weak gravitational lensing studies, mapping the distribution of dark matter at cosmological scales. The observatory is named for Vera Rubin, whose work on galaxy rotation curves provided some of the strongest early evidence for dark matter, the invisible mass whose gravitational influence underlies the very flows that define structures like Laniakea. The third development is the continued Cosmic Flows program. Tully's group at the University of Hawaii, having built the Cosmic Flows series into one of the most comprehensive galaxy distance catalogs available, continues to extend it. Each update incorporates new and more precise distance measurements from multiple indicators: the Tully-Fisher relation for spiral galaxies, the fundamental plane for elliptical galaxies, surface brightness fluctuations for nearby ellipticals, and type Ia supernova for more distant systems. The combination extends the catalog's reach and improves its precision at the intermediate distances most important for characterizing the boundary between the Laniakea and Shapley basins. The fourth development is in theoretical modeling. Cosmological simulations of large-scale structure formation have become sophisticated enough to produce simulated local universes that resemble the observed environment, with features analogous to Laniakea and the Shapley concentration appearing in the simulated cosmic web at roughly the right scales. These simulations can be used to test whether the observed peculiar velocity field is consistent with the expected properties of a Shapley-centered basin, and to determine which additional observations would be most diagnostic. The convergence of DAISY, Rubin, the ongoing cosmic flows work, and improved simulations means that the question of whether Laniakea is a sub-basin of a larger structure will likely be addressed far more definitively within the next decade. We are close to the next answer, and given the history of this story, every answer a door to a bigger room, the next answer may itself raise the next question. The story of the Great Attractor has a future as well as a past. Not in the sense of the Milky Way's eventual motion. The trajectory we are on is set for billions of years, and neither the Great Attractor, nor Laniakea, nor the possible Shapley Basin will change in any meaningful way on timescales relevant to human civilization. The future is in what the Great Attractor story teaches us about how to understand our place in the universe, and what the next generation of surveys will reveal. The most immediate implication is for our cosmic address. Every generation of astronomical discovery has added a line. Earth orbits the Sun in the solar system. The solar system sits in the Milky Way galaxy. The Milky Way is a member of the local group. The local group is part of the Virgo cluster's sphere of influence. The Virgo supercluster is part of the Laniakea supercluster, and Laniakea may be part of a larger structure centered on the Shapley concentration, whose name, if the 2024 analysis is confirmed, will need to join the list. This is not just an academic exercise in taxonomic completeness. It matters because each layer of the hierarchy shapes the gravitational environment of everything within it. The dynamics of the Milky Way are influenced by the dynamics of the local group, which are influenced by the Virgo cluster, which are influenced by the broader flow patterns of Laniakea. Understanding the full hierarchy is understanding the full context of our cosmic existence. The second implication is for cosmological modeling. The large-scale structure of the universe, the cosmic web of filaments, walls, and voids, is the product of billions of years of gravitational evolution, starting from the tiny density fluctuations of the early universe. The distribution of matter in the local universe, including Laniakea and the possible Shapley Basin, encodes information about the initial conditions of the universe and the physics that governed its evolution. Measuring this structure precisely provides some of the most direct tests of the standard model of cosmology. The third implication is for the long-term future of the universe. Laniakea will not always exist as a coherent structure. Dark energy is driving the accelerating expansion of the universe, and over timescales of tens to hundreds of billions of years. The structures of the cosmic web will gradually be stretched and dispersed. The only structures that will survive as gravitationally bound objects are those dense enough to resist the expansion: individual galaxies, galaxy groups, and galaxy clusters. The local group, the Milky Way, Andromeda, and their smaller companions will remain bound over the next several billion years. The Milky Way and Andromeda are expected to merge into a single giant galaxy. That merged system will persist as a gravitationally bound object for the indefinite future, even as the rest of Laniakea's 100,000 galaxies drift away, carried by the expansion to distances too great to observe. In the very far future, that merged galaxy will sit alone in its local universe, surrounded by an expanding void, cut off from all other galaxies, unable to see the broader structure it once belonged to. The cosmic web will have been erased from any local observer's view by expansion. Laniakea will exist only as a historical record, if any civilization is around with access to records from the current epoch. We are alive in the era when the cosmic web still exists, when the structure of Laniakea can be mapped, when the Great Attractor can be identified, when the question of whether we belong to a Shapley Basin can be asked and answered. That is not a small thing. We exist at a specific moment in the history of a structure that will not always be here to be observed. What we are learning now about the shape of the universe we inhabit is knowledge that will not be available, in the same way, to any civilization that comes long after the cosmic web has been dispersed by dark energy. We are not just inside Laniakea. We are inside Laniakea at the right time to know it, and here is what makes all of this truly remarkable. When the Seven Samurai named the Great Attractor in 1988, they were naming something they could not see. They were naming a gravitational effect, a pull on the motion of hundreds of galaxies, across hundreds of millions of light-years, pointing toward a region of sky that the Milky Way's own disk was hiding from them. They gave a name to an absence, a name to something they could measure but not observe, and they were right. Something was there, something enormous, something that, when it was finally revealed, through decades of observation, through the piercing of the zone of avoidance, through the cosmic flows surveys, through the definition of Laniakea, turned out to be not a single object, but a place. Not a thing, but a topology, not a mass, but a convergence. The Great Attractor is the center of a gravitational watershed containing 100,000 galaxies, spanning roughly 500 million light-years, inside which we have always been living without knowing it. Let that sit for a moment. Every human being who has ever lived, every civilization, every story, every moment of consciousness that has occurred on this planet, has been inside the Laniakea supercluster, being drawn, slowly, toward its gravitational center, moving at hundreds of kilometers per second toward a place that, because the universe is expanding faster than we can travel, we will never actually reach. We are passengers inside a structure so large that light would take hundreds of millions of years to cross it. We are moving toward a center that is simultaneously receding from us as the universe expands. We are part of a structure that is itself, with roughly 60% probability, falling into something 10 times larger, a structure whose edges we are only now beginning to see, and whose full extent may lie beyond the reach of current instruments. And we have been inside all of this the entire time, not moving through it, not visiting it, living in it. This is our home. This is the address of every star in the night sky, every galaxy in the Hubble Deep Field, every civilization that may exist anywhere in the local universe. Laniakea, immense heaven. We did not know we lived there. We discovered it by watching which way the galaxies moved, reading the slope of a gravitational landscape we could not directly see, inferring the shape of a room we had never stepped outside of. And now we know. The Great Attractor is not a mystery anymore. It is our center, our anchor, the gravitational low point of the structure we have always called home, even when we had no name for either the structure or the low point. The mystery behind the mystery behind the mystery is still being mapped, but we are reading the shape of it, survey by survey, galaxy motion by galaxy motion. The room is vast, we are small inside it. And we are the only creatures in this room, as far as we know, who have ever stopped to ask what the room is called. But there is one more piece to this story. Because, if Laniakea is falling toward the Shapley concentration, and the 2024 data suggests a 60% probability that it is, then the Shapley concentration is one of the most important structures in the nearby universe. Not just gravitationally, but scientifically. It is one of the places where the predictions of our cosmological models are most directly confronted with data, and there are specific aspects of the local large-scale flow field, and of how much mass is required to produce the motions we observe, that do not fit the standard model as cleanly as cosmologists would like. Some of those questions connect directly to the Hubble tension, the persistent, unresolved disagreement between different ways of measuring how fast the universe is expanding, which is one of the deepest open problems in modern cosmology. That is a story for next time. Tonight, we did not just learn about a gravitational pull on our galaxy. We traced the history of a discovery that took 40 years to complete, and may not be complete yet. We saw astronomers in the 1970s noticing that galaxies were not moving the way they should. We watched the Seven Samurai in the 1980s, pooling their data, measuring the motions of hundreds of galaxies, finding a coherent flow that no known structure could explain. We watched them name something they couldn't see. We watched the Zone of Avoidance slowly yield its secret. Through X-ray satellites and radio surveys and infrared cameras, revealing the Norma cluster and the Hydra Centaurus concentration that had been hiding behind our own galaxy for the entire history of astronomy. We watched Brent Tully and his colleagues, in 2014, redefine our cosmic address with a single paper, showing that the Great Attractor was not an isolated anomaly, but the center of a supercluster we had been living inside without knowing it. Laniakea, immense heaven. And we watched, in 2024, the possibility emerged that even Laniakea is not the final layer, that we may be part of something 10 times larger, centered on the Shapley concentration, whose edges we cannot yet see. This was a story about a question that kept expanding. Every answer was a door to a bigger room. That is not frustration. That is the most honest description of what it means to study the universe at the largest scales we can reach. Even now, with the best galaxy distance catalogs ever assembled and the most sophisticated analysis methods ever applied, the picture is not complete. We do not know whether Laniakea is a sub-basin of a Shapley-centered structure. The 60% probability from the 2024 analysis is a probabilistic inference from incomplete data. The answer requires Dacey scale and Rubin scale surveys that are still being assembled. We do not know the precise mass of the Great Attractor region, the Norma cluster, and the surrounding structures, the dark matter halos and intergalactic medium that contribute to the gravitational landscape but are not directly observable. We do not know whether there is a structure larger than the Shapley Basin in our cosmic neighborhood. The 2024 analysis itself hints at one, in the Sloan Great Wall Basin, or where the nested hierarchy finally ends and dark energy takes over. And we do not know, in the deepest sense, whether our location inside Laniakea is typical of where galaxies like ours tend to sit in the cosmic web, or whether the specific configuration of our neighborhood is unusual in ways that have shaped the history of our galaxy. These questions are open, the surveys continue, the data accumulates, the answers will come. There are a few things worth taking from this story that go beyond the Great Attractor itself. The first is that we have always been inside the structures we discover. Laniakea existed before we knew about it. The Great Attractor was pulling our galaxy before we had a name for it. Discovery does not create the thing discovered, it changes what we know about where we are. The universe does not wait for us to map it before it operates. The second is that the zone of avoidance is a reminder that our own presence in the universe creates blind spots. Our galaxy's disk, the very structure we live inside, was hiding the most important gravitational feature of our local universe from us for the entire history of astronomy. What other structures are we missing because our own location in the universe obstructs the view? The third is that scale changes meaning. At the scale of a solar system, the Great Attractor is irrelevant. Its gravitational effects on the solar system are negligible. At the scale of the local universe, it defines our address. The same physics produces structures at every scale, and understanding those structures requires being willing to look at the appropriate scale, rather than defaulting to the one that feels most familiar. The fourth is that every answer in cosmology has been an expanded question. The Milky Way was a galaxy. The galaxy was part of a cluster. The cluster was part of a supercluster. The supercluster was part of a larger supercluster. The pattern suggests humility about what the next answer will contain, and the fifth is this. We are the only creatures in this room, as far as we know, who have ever stopped to ask what the room is called. That is not a small thing, that is everything. So, I want to leave you with a few questions tonight. What does it feel like to know that the entire Milky Way, every star in the night sky, has been inside the Laniakea supercluster the whole time, moving toward a gravitational center that is simultaneously receding as the universe expands? Does knowing the name and shape of the structure we live in change how you experience the universe around you? When we look at the nested hierarchy of attractors, local group, Virgo cluster, Laniakea, possibly Shapley, and see that every answer has been a sub-answer within something larger, what does that tell us about the question itself? Is there a final answer, a largest structure, a bottom to the hierarchy? Or does the universe keep going, basin within basin, attractor within attractor, all the way to the horizon of what we can observe and beyond? Sit with those questions for a moment. They are not rhetorical, they are the leading edge of what cosmology is actively working to answer. If this story stayed with you, tell me in the comments which moment was the one that pulled you in. Was it the 7 samurai naming something they couldn't see? The zone of avoidance finally yielding after decades of frustration? The 2014 Laniakea discovery that we have always been inside a supercluster? Or the 2024 finding that even Laniakea may be a substructure within something 10 times larger that we haven't finished mapping? I want to know. And if you want more stories like this, the grandest scales of cosmology, told clearly and honestly, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one. The Milky Way is moving toward the center of a supercluster, whose edges we are still learning to see, which may itself be falling toward a structure whose edges we cannot yet see at all. We named the Great Attractor before we found it. We found Laniakea before we knew we lived in it, and we are only beginning to understand the shape of the room that contains them both. That is the universe, that is home.